Hi everyone. Yesterday we talked about the real SVM with a polynomial kernel. And for the polynomial kernel, well, before we discuss the polynomial kernel, well, we first say one of the way that we can do better classification is we introduce polynomial features. And to introduce polynomial features, we are adding different degrees of the polynomial features into our data set, and that is expensive, right? And then we say for the polynomial kernel, it can do the similar thing and give us the similar results without actually adding those polynomial features. So using the polynomial kernel, it can be a little bit fast, but still we want to be careful. We don't want to use very high degree of polynomials because that still will slow down the system a lot. Okay, and today we are going to want to talk about a new kernel, and well, this is called the RBF kernel, and usually I prefer to call that just Gaussian kernel. So for the Gaussian, well, Gaussian is nothing but a bell-shaped curve, right? Like this one. So what we are doing is, first, we are going to still use the same data set with only one dimension, that is x. Okay, so only one dimension, and we have green samples in the middle, here, and then for the blue samples we have them on both sides, and that's a problem. So we have two samples on the left side, two samples on the right side, and if you want to do a linear classification, it's not doable. And instead of doing the polynomial features, now we have another idea. How about we pick two samples? So we pick this sample -2 and another sample 1, and then we draw two Gaussian curves. Okay, so in the center of the -2 and on the center of the 1, we draw two Gaussian curves. And after that, for each of the sample, we calculate the distance between that sample to two of those Gaussian curves. So for for example, like this one. So for this green sample, the distance from this sample to the green curve will be this one, roughly 0.25. And then the distance between this green sample to the blue Gaussian curve is here, so that is 0.75. Okay, and then we can map this sample to a new different dimension using the distances to the green Gaussian curve and the blue Gaussian curve. And then if you're considering this one, and the distance is 0.25 and 0.75, right? And then if you want to find that, it is here. Okay, so this means we are 100% throw away the original feature x. Instead, we are using the distances to the two Gaussian curves as x1, x2, and x3, and then using the x2 and x3 as the x and y axis. And now we can say, okay, we find a linear cut or a linear boundary, right? So this is just the other idea of doing the classification. We are trying to again introduce some of the new features and then make the samples linearly separable. Okay, so that is the basic idea of the Gaussian kernel or the RBF kernel. And another thing we want to discuss is, well, when we are drawing the Gaussian curves, and there is a very important hyperparameter called gamma. Okay, so here, if we draw a Gaussian, oops, where's my pen? Okay, so if we draw a Gaussian curve, it can be like this. So this is a very, very fat Gaussian, right? So the center is here. And well, we can also draw a much skinnier Gaussian. It should be like this. So how do we control how fat a Gaussian curve can be? So, well, we can do everything the same except for how fat the Gaussian curves can be. And then we can also control that by specifying the gamma. And that is a very important feature in the Gaussian kernel. Okay, and the next question is, how do we choose the landmarks? So for the landmarks, I mean the -2 here and the 1 here, and those two landmarks, they are the center of those two Gaussians, right? So we pick two samples and then we draw two Gaussian curves. And why do we pick those two samples? And how do we pick the right centers or the right landmarks and draw the Gaussian curves? And actually, we don't know that. So we have to draw the Gaussian curves on all the features. Let me say it again. We have to draw the Gaussian curves on all the samples. So we have, well, probably nine samples. So in this case, well, the real way to deal with to do the Gaussian kernel is we have to draw the Gaussian curves on all the samples, and that's a lot. And yeah, that's right, that's a lot. And the point is, well, this is again going to be computational expensive, because say if we have n samples and then we have to draw n Gaussian curves, and for each of the sample we have to calculate the distance between that sample to n Gaussian curves. So we are introducing an additional n by n matrix to the existing feature space. Okay, that's really a lot, because n is the number of the training samples. Okay, so that's the reason that doing the Gaussian kernel, that's also a computational expensive task. Okay, so well, let's just do a very short example. We still make the moons. We make the two moons like this, and after that we use the standard scalar. And remember, as long as you are doing the SVM, you always need to do the standard scalar, and we just create a SVM model with the kernel as a RBF, and that is the name of the Gaussian kernel, and we specify the gamma to be 5 and the C to be a 0.001. And the next part, we want to talk about gamma, and we want to see what is the difference between a high gamma and a low gamma. Okay, so we are trying, well, the first thing is there are two parameters we can try. So we can do the gamma and then we can do the C. So those are the two hyperparameters we have to specify when we are doing the Gaussian kernel. And if we do a very small gamma and a very small c, it is what? It is a linear boundary, right? So on the upper left, what we really see is, using the Gaussian kernel with a very small gamma and very small c, we got a linear boundary. And what is that? Is that a overfit or a underfit? It is an underfit. Okay, so because we didn't really capture the structure of the boundary of those two classes, and we did the easiest thing, which is a linear cut. So for the linear cut, it is not 100% wrong, but we didn't capture the difference, the curvy boundary. Okay, so well, that is an underfit. So for the gamma, a very low gamma and a very low c, both of them may contribute to a underfit. So why? Especially for the gamma. So this one is the low gamma. So we are having a very fat Gaussian curve, and then no matter our sample is here, sample is here, and or sample is here. So well, the distances between those samples to the low gamma Gaussian curve are not that differentiable. That's a problem. Okay, so okay, it should be sample 3 in this case. So well, remember, for both of the low gamma and low c, we end up with a underfit model. And how about this one? How about the lower right one? So for lower right one, and it doesn't make too much sense for me either, even though it is a good classification, and I really hate this part, right? So for this corner, why it is classified to be green, and it doesn't make any sense to me. So, well, when we are doing a very high gamma and a very high C, and remember both of them may contribute to a overfitted model. So for this case, I won't say the overfitting model is that bad, but still I will say that is a overfitted model. Okay, so well, this is the basic idea on how you want to control the gamma and the C. So you don't want to make it a very high or very low. So usually the general rule is, well, when we are doing the grid search, we'll try the 10 powers 10 powers negative 3 to 10 powers 3, and that should be a reasonable range. If you go even higher or even lower, and then that is risky. Okay, so and here is another review of the hyperparameter C. So for the C, if you get it very low, and then the descent surface is smooth, and then you may have the underfit model. And if you have a very high C, and then it will learn very hard from the training data set. However, and you may have a overfit model. Okay, and this is another comparison of the different combinations of the low gamma and the medium gamma and the high gamma, and also the low C, medium C, and the high C. Okay, so again, on the upper left, if we have the low gamma and the low C, and then we have a linear decision boundary or a linear margin, so we didn't really capture the curves of the decision boundary. And if you see this one, if you do a very high gamma and a very high C, and the problem is we are learning only on the training samples. So for the outside, so if you see here the blue shade and the red shade, well, it means even though there's no sample there, as if we see a testing sample, we are very confident it belongs to either the blue class or the red class. However, for this one, if you just point here, how do we classify that? And we don't know, because for this overfitting model, it learns very hard towards the training data set. And as long as you give that a new sample which is far away from any of the training samples, and then it will get confused. Okay, so you don't want to have the overfitted, and you don't have to want to have the underfitted sample, overfitting model. Okay, so well, the next part we are going to do another research, and we will have another exercise. So I will see you on the next video.